Hello and welcome to Module 2 of Kubernetes for Services and Care Engineers Level 3 certification. In this module, we will talk about Kubernetes objects. Here is a high-level overview of the different sections of this module and their objectives. We will start by explaining the most fundamental Kubernetes objects like pods, deployment, services, and jobs. We will understand the purpose of each object type and how we can create and use them. Then we will describe the microservice-based application architecture. We will continue with a couple of hands-on demos in which we will experiment with Kubernetes objects, and we will learn how we can create those objects and modify them using the kubectl tool of Kubernetes. And we will end the module with a quick summary of the topics covered in this module.
In this section, let's see what are Kubernetes objects. So in Kubernetes, everything that you create in a cluster is an object. So let us see the simple definition. A Kubernetes object is an entity provided by Kubernetes for deploying, maintaining, and scaling applications on the Kubernetes cluster. So what are the examples? So these are the examples of objects. So a pod, service, deployment, a config map, a secret, an account, a role, a volume, all these things are objects for Kubernetes. That's why I said in the beginning that anything that you create as a part of your application is an object for Kubernetes. So when you create a whole application, you basically create a combination of these objects. So an application will contain definitely some pods, and along with the pods, it may contain a service, it may contain a config map, it may contain a volume, some secrets, or depending on the requirement of the application, any object it may contain, right? So all these things are objects for Kubernetes. If I go with the official definition, a Kubernetes object is a record of intent. When I say record of intent, that means your cluster's desired state. Okay, what your Kubernetes cluster wants to do finally. Okay, so you are effectively telling the Kubernetes system what you want your cluster's workload to look like. Okay, so that's the declarative nature of the Kubernetes, that you declare an object and Kubernetes itself tries to maintain that desired state of the cluster now. Okay, if you want to see how many type of objects exists in Kubernetes, so this is the command to see that: kubectl space API hyphen resources. Okay, we will see the output in our cluster. So there are two methods to create an object. Okay, the first one is via command line. So this is the command to create a container, to create a pod basically, and the dry run and the OYAML options are highlighted in front of you. You have to remove them. So as soon as you run this command, this kind of configuration will be created inside your cluster, which you can check via the edit command. And the second method is via YAML file. So you have to have that YAML file available in your cluster first. You upload that YAML file and you give kubectl create-f. Okay. In the YAML structure of any Kubernetes object, these highlighted sections are the four main fields of any Kubernetes object. So API version should be there. Okay, so this is you just copy this API version from the sample YAML page. You don't have to apply your brain what API version stands to where. Okay, kind is the field which will tell you which kind of object it is. For example, this is a deployment kind of object. Okay, metadata is information about this file. So the name is nginx deployment. So for this deployment, the name is nginx deployment. And comes the most important field, which is the spec section. So specification contains all the specification of this object. So you see these are deployment specification, and inside deployment you have containers specification also. Okay, and nobody writes these files manually, so don't worry. These files are either created by some automated tools, or every yeah, YAML, every sample YAML is available in the Kubernetes documentation page. You can copy from there and modify only those fields, only those words or letters which are required as per your requirement in the application. Okay, so we will understand the structure later as soon as we understand different objects. Right now, just understand that without, if any of these four fields are missing or incorrect, then your object cannot be created. Okay, these are mandatory fields. Let us see about Kubernetes namespaces now. Namespaces is an old Linux concept which are basically a logical separation of the resources. In Kubernetes also, we have the same concept. That means if I consider Kubernetes cluster as a big room, as a big house, then the namespaces are the small rooms, okay, which somehow isolate the environment of one room from another. So namespaces provides a mechanism for isolating groups of resources within a single cluster. If worker nodes provide physical separation, then namespaces provide logical separation in a cluster. This means namespace can span across different worker nodes. Okay, they are not limited to any specific worker node only. So here K8's Kubernetes node is written, it should be Kubernetes nodes. That means the namespaces can be on different nodes also. Okay. So for example, in a cluster, if you have, let's say, developers also working and your QA testers also working and some other users also working and creating their own resources, then you can have separate namespaces for them in which they can create their resources so that their resources will be isolated in that namespace only. So as I said, it is like separate rooms in a big house for isolation or separation. Names of resources need to be unique within a namespace, but not across namespaces. This means I can have a pod named Nginx in this namespace and pod named Nginx in dev namespace and in QA namespace also. But I cannot have two pods with the same name in the same namespace. Okay, so I cannot have two Nginx pods in any of the namespace, but I can have them in different namespaces. So that uniqueness has to be maintained as per the namespaces only. And there is a default namespace if you don't specify it. So this is the one which is default namespace. Okay. In this section, we will discuss pods. Because we are discussing Kubernetes objects, so it is necessary to discuss pods at a very first place. If I talk about pods, then I would like to tell you in the beginning that all these objects finally create pods. That means the final product of a deployment is pod. The final product of a daemon set is a pod. Static pod is also a kind of pod. And when you create stateful sets, they also create pods. And separately, you can create pods itself as an object. Okay, but all these objects have different purpose in Kubernetes. That means you cannot create a deployment where you need a daemon set. You cannot create a daemon set where you need a static pod, and similarly stateful set. So the purpose of every object is different, but finally they create pods on the Kubernetes cluster. That's why it is very much necessary to understand what is a pod. So as we have understood earlier also that if this is a container, then this is a pod. So what we do, Kubernetes does not deploy containers directly on the worker nodes. The containers are encapsulated first into a wrapper, which is known as a pod. And I told you the reason why. Because a pod is easier to handle than a container itself. Okay, the Kubernetes attach an IP address on pod level, and all the containers inside the pod can be accessed via different port numbers, but the IP will remain same. So a pod is a single instance of an application. A pod is the smallest object that you can create in Kubernetes. It is also called as the building block of Kubernetes. Any container in the same pod will share the same resources like CPU and RAM and the local network, which means the IP address. Imagine this is a three-layer web application. There is a web server, there is a database server, and there is a messaging app, which is the part of the application itself. So if you want to deploy this application via containers, so basically uh, every application is running inside a container. Okay, inside a container means a separate pod with its own container image as a Docker image. Okay, so we will have a separate Docker image for the web server, which might be developed into Node.js. Okay, and we will have a separate Docker image for the MongoDB for the database. Okay, and we will have a separate Docker image for the messaging app. And every image will have its own dependencies. That means libraries and binaries. Okay, any packages if are required. And these three containers we will create on the Kubernetes cluster and will connect them via internal network. So all these three pods together will be called as an application, three-layer web application. Okay, this is just a simple explanation. It will contain more objects than simply the pods. Now let us talk about deployments. So deployment is just another object like pods, but it serves a great purpose than the pods themselves. So in any production environment, whenever we want to create pods, we will create them via deployments. I mean, generally, the pods will be created via deployments. Why? So a deployment's primary purpose is to declare how many replicas of a pod should be running at a time. Okay, that means we can create multiple replicas of a pod using deployment, because a single instance of a pod cannot serve the purpose in the production environment. So we always require multiple replicas of the same pod, and those replicas will be controlled by the deployment object. So when a deployment is added to the cluster, it will automatically spin up the requested number of pods and then monitor them. If a pod dies, the deployment will automatically recreate it. So that's one of the greatest advantage, that if let's say there is a problem with one of the pods, then the deployment will automatically recreate it. You do not have to worry about the recreation manually. And there are some operations which can be performed only on a deployment and not on pods. So what are those operations? For example, scaling up or scaling down the pods in production environment, like increasing the number of replicas or decreasing it. It is only possible via deployments. Deployment automates rolling updates or changes to pods, for example, software upgrade or image upgrade without any downtime of the application. Okay, so this is not possible in a single pod instance, but with deployments, you can upgrade the software without any downtime, which is one of the key features of applications running on Kubernetes, that you can upgrade the application without any downtime because you have multiple replicas. Deployments can upgrade image one by one in all the pods, so that you always have some pods catering to the traffic and some pods getting upgraded at the same time. A revision history is maintained also, and there is a support for rolling back to a previous version. So let us understand another object in the same series, which is daemon sets. So daemon set is also an object which will finally create pods on the system. But the purpose of daemon sets is different from deployment. Okay, so what is the purpose? So a daemon set ensures that all nodes run a copy of a pod. As nodes are added to the cluster, pods are added to them, which means if I want to have a pod and I want the one copy of a pod per node. For example, let's say I have 10 nodes. So I want one copy of that pod to be run on every node. In that case, I will not create that pod as deployment. I will create it as daemon set. I mean, the property of daemon set is that as soon as you create a daemon set, okay, so inside the daemon set, you will have the pod specifications inside the daemon set, okay, and as soon as Kubernetes detect that there is a daemon set being created, so it will automatically create one copy of that pod, of that container, into all the nodes that are part of the cluster. Okay, so daemon sets attempt to adhere to a one pod per node model, either across the entire cluster or a subset of nodes also. So this is also possible that you group your nodes via some labels, and you want a copy of a pod into a particular group of nodes. So that can also be done from daemon set. Okay, and you must be thinking, what is the use case for this? So a use case is like monitoring solutions, logs viewer. So for example, fluentd is a logs solution. Okay, it is an agent which performs some logging, reporting to the cluster, okay, from the nodes. So what we will do whenever this kind of solution is we are going to deploy into the cluster, so we have to have that agent available in all the nodes possible, right? So we will create them as daemon sets and not as deployments. So the next object in this series is static pods. Okay, so static pods is also a kind of pod, and it has a specific function. So at times it is required that some pods should be controlled by the kubelet itself in the worker node. I mean, generally, all the pods are controlled by the kube controller manager, which is there on the master node. But at times, you need some functionality that the worker node itself should be able to control a pod, right? And the kubelet should be able to manage it. Okay, so inside the kubelet, there is a path generally which is etc Kubernetes manifests. Not inside the kubelet, I mean inside the worker node. If you go to this path, etc Kubernetes and manifests, and if you place a pod.yaml file, that pod will be automatically created in this worker node, and it will remain in this worker node only. Okay, that means no control of the master node is required to manage this pod. Okay, so static pods are managed directly by the kubelet daemon on a specific worker node. Remember, okay, directly by the kubelet daemon. I mean, they do not have any interference of the kube controller. Okay, they are visible on the API server. I mean, if I do kubectl get pods, then these pods will also be visible, but they cannot be controlled from there. I mean, you cannot perform any operation on these pods via kubectl from the master node. If it fails, the kubelet will restart it. Okay, and they are bound to one kubelet on a specific node. That means they cannot move onto other worker nodes. If their YAML files, if their manifest file has been placed inside a specific worker node, they will be bound to that specific node only. And only pods can be created this way, no other objects. That means you cannot create a static replica set. You cannot create a static deployment. No, only pod as an object you can create as a static pods. Okay, so you must be thinking, what is the use case for these static pods? So the use case is control plane components that are bound on a specific node, like kube proxy in the worker node. So we all know that uh, kubelet and kube proxy are control plane components, right? And kube scheduler, kube API server, kube controller, etcd, these are all the parts of master node. Okay, but how they are created? Okay, so but if you check this file in a private data center, in a private Kubernetes cluster, etc Kubernetes manifest folder, if you check, so you will find that etcd.yaml, kube API server.yaml, kube controller manager.yaml, and kube scheduler.yaml. These YAML files, these components are created actually as static pods in the master node. So in master node also you have kubelet, remember. Okay, in master nodes also you have kubelet, but you the system will not schedule normal pods there. Okay, but these components with their YAML files are actually created under this path, static pod path, etc Kubernetes manifests, so that whenever the master node gets boot up or master node gets created, all these components will be automatically created with them. Okay, so any component that you want to create uh, I mean without the kubectl or the kube API, okay, so you have to create it via static pod, as a static pod actually. Okay, so that's how these components spin up, and later on we use them to create other objects. So this is one of the typical case of use case of static pods. There can be some other use cases if you need in any application which whose control you require, I mean apart from the master node, you can create them as static pods. So I told you that these are the objects which finally create pods. So pods itself create pods, yes. We saw deployment. Deployment creates replicas of pods. Daemon set creates one copy of a pod per node. Okay. So there is no fixed number of replica, but as many number of nodes are there, that many copies will be created. Okay. One copy of pod per node. Static pod we just saw finally create pods, but in a different way, directly on the worker node managed by kubelet. So the last object that is left is now stateful set. Okay, but I am leaving this topic here because we will learn stateful set when we will learn storage concepts in Kubernetes. So it requires some understanding of storage. So when we will learn storage, then we will come back to stateful set. In this section, we will talk about Kubernetes connectivity basic principles. I mean, this is not advanced networking, but some basic principles of Kubernetes connectivity which is required to proceed further. In any Kubernetes cluster, we have two networks, a host network and a pod network. A host network, as you can see, is a big network chunk out of which smaller subnets have been allocated to every node. So this is a big network, 172.17.00/16, and 1.100, 2.100, 3.100, like this we can separate some smaller subnets to different nodes. Okay. Inside the nodes, we have pods, and the IP addresses of the pods will be allocated from the pod network. So inside node, you have another network which is called as pod network. So if you see, there is a big pod network subnet available outside, and further subnetting has been done to accommodate enough pods in every nodes. So /24 IP, for example, has been given to different subnets so that each of them can accommodate 254 pods. So you see, every pod in a node has IP address from that pod network only. So this is 196.1 series, this is 100.96.2 series, this is 100.96.3 series. This is just an example. The actual values might be different onto your cluster. Okay. So by default, always remember these three rules in Kubernetes. All nodes can communicate with each other. That means ping between nodes will work. Okay. All pods can communicate with each other. That means every pod can ping to every other pod. And also all nodes can communicate with all pods. That means ping between pods and nodes will also work. Okay, so these are three basic connectivity rules by default. So now when we have understood uh, pods and nodes IP addresses, so there is one more thing which needs to be understood. See, pods IPs are ephemeral. By ephemeral, I means temporary, which can be changed. And they change as soon as a pod is recreated. So as soon as a pod is deleted or recreated, which is quite a normal activity in a Kubernetes cluster, their IPs are gone. So you you cannot rely on pod IP addresses to communicate within your applications. So application needs something static to communicate between them, and that's when services comes into picture. So the other object that we are going to learn are Kubernetes services, and that's why this background is being given. Okay, so assume a three-layer web application wherein you have one deployment for your web server. Okay, so one deployment with three replicas for your web server, another deployment for your backend server application. Okay, so backend application is another deployment with three replicas, and another deployment is, let's say, your database with three replicas. So you have three web servers, three backend web components, and three databases. Now every pod, these are basically pods. So three pods of web, three pods of backend, three pods of DB. Every pod has to communicate with themselves, with each other, right? But these pod IP addresses are temporary. So how can we communicate with these components? So we need something which is called as services. So now we will create front-end service, back-end service, and database service. Okay, so service is nothing but a virtual IP allocated for the pods and bound to it. So this is a service, that means this is a virtual IP, and this virtual IP will be bound to all the web pods, all these three web pods. I mean, this will make a load balancing in itself. We just have to reach to this IP address. Once we reach this service IP address, we can reach to the web pod. Okay. Similarly, the web pod, when they wants to talk to the backend application, they will reach the backend service IP address. So the service IP remains static and unchanged. The service IPs do not change. They remain static. Okay, and when the backend pod wants to communicate something to the DB, they will communicate to the database service, to this static IP address, to this virtual IP address, and the information will automatically be get transferred to the DB. Okay, so that's when services comes into play, and the next object we are going to study is Kubernetes services. So if I compare this diagram with the current telco analogy, then this will be a very interesting comparison. See, uh, right now in the VNFs, you have these kind of VMs working generally in any telco VNF. So first and foremost, we have some LB which we called as load balancer virtual machines, right? Generally, this is a pair of VM. And then you have some OEM VMs. OEM VMs are also in pair, redundant. Then you have some line cards, which works in N+1 redundancy. And finally, you have some DB VMs. So at last, whatever information is being processed, its state gets stored into this database, right? So these kind of VMs together constitute a VNF right now, okay, under virtual machines. When this was containerized, this architecture was containerized into Kubernetes, then this is going to have this correspondence. How? So instead of LBVMs, now we are going to have a load balancer service in Kubernetes, which will load balance and provide an access to the front end component. Okay, so the front end component right now is the O&M. So you can consider this web pods as your O&M VMs now. Okay, and further, O&M wants to talk to line and line wants to talk to DB. So they have further services available. Okay, so right now these are connected via internal networks. Similarly, these pods and services will also be connected via internal networks, which we will see in detail when we will study Kubernetes networking. Okay, so that's how you can compare the current analogy of VM-based architecture into Kubernetes. In this section, we will learn about Kubernetes services. So services is just another Kubernetes object, just like pods or deployment. Services are required to communicate between deployments or between the pods. Okay, so as we understood, like a service is a virtual and static IP which doesn't change over a period of time. So let's assume this three-layer web application again. wherein you have a web server as your front-end pods, then a back-end pod set, and a set of database pods like Redis. Okay, you as a user sitting outside a cloud cluster. Okay, outside in the cluster basically. So if you want to communicate to this application, the front-facing component with which you can communicate is the web server only. Like you cannot communicate directly with the database or with the backend pod. So there is always a front-facing web server of all the applications, and generally it is a web server. So if you want to communicate with the web app or the web server, you will communicate through a specific type of service. Okay, that will be called as load balancer here in this case. And there are some other specific type of services which are required to communicate internally within the software components. So we will understand these different types of services here in this slide. So there are three types of Kubernetes services, and they are called as cluster IP, node port, and load balancer. As the diagram depicts, this circle, this shaded circle represents the service. Okay, so cluster IP is basically to communicate within the application, and that too inside the cluster. Okay, so as the circle seems to be inside this rectangle, and this rectangle you can assume a Kubernetes cluster. So this service is used to communicate within the application and inside the cluster. Now I'll come to the third type of service first, which is the load balancer. So as you can see here, if this is a cluster, then the load balancer service is outside the cluster. Okay, so this is a standard way to expose an application to the internet. Why? Because via the load balancer service, you talk to the application or you communicate to the application from outside the cloud or outside the Kubernetes cluster. So that's why this service is always outside the cluster. And there is another way to communicate from outside the cluster with the front-facing application component, which is called as node port service. Okay, so we will understand these three types of services in detail, one by one, in their specific sections. So now if I talk about the definition, so service is a way to expose an application running on a set of pods as a network service within or outside the Kubernetes cluster. A service is bound to a pod or a deployment and acts as their virtual IP. So as many pods associated with the deployment, the service will act as a virtual IP for all those pods. A pod acts as endpoints to a service. Or, or if there are number of pods in a deployment, then all of them will act as endpoints to a service. Now, to, to know more about services or to dig deep before digging deep in them, I mean, we should understand some ports description of services. So if this is the YAML file of the service, okay, so in this YAML file you see the kind as service. Okay, so in this YAML file you will see there are some ports defined, a port, a target port, and maybe a node port also. Okay, so if you consider this as a worker node, and inside a worker node you have a pod and you have a service also. All those services are a cluster wide concept. So service exists, I mean, in all the worker nodes, wherever your pods get scheduled. Okay, so there is a service, there is a pod, and as a user, if you want to communicate to the pod, you will actually communicate to the service with an IP address and a port number, and that IP address and port number will be mapped in the background to the pod and its port number. Okay, so always remember the ports from the viewpoint of service and not from the viewpoint of the pod. So here, if you see from the viewpoint of a service, this is a target port. Okay, although it is a normal port for the pod, But from the viewpoint of a service, this port 80 is a target port. So that's why target port is 80 here. Okay, and service's own port address, which is 7500 here, is the port. Okay, so do not get confused with this port and target port. If the YAML or the configuration is of a service, kind service, then the target port will always be the port number of the pod, and simply the port is the port number of the service. So you see that the service IP address range and the pod IP address range are completely different. And this port here, like if you are coming from outside the cloud, you must need a port for the physical worker node also to enter it, right? So the port of the physical node or the worker node is called the node port. Okay, so that's how these three ports are arranged. Now let us understand in detail about the cluster IP service. So see this diagram again. So we have a web UI or a web server, and this web server, if wants to communicate with the backend pod, then it has to communicate via a service, and that service will be of cluster IP type. Similarly, if the backend pods wants to communicate with the database pods, then they can communicate via a service, and that service will be of cluster IP type. But why? Because this communication is within the cluster. That means this web UI is communicating to backend pods, and these backend pods also exist within the same Kubernetes cluster. And the database pods also exist within the same Kubernetes cluster. So as I told you, the first definition of cluster IP, that this is used to communicate between the components within the Kubernetes cluster. So here is a sample of a service YAML file, and you see the kind is service. So the kind will not differentiate between cluster IP or load balancer or node port. So for all three of them, the kind will remain service. Okay, what what will differentiate them is the type, which will be mentioned here somewhere. Okay, so in this sample, you will see that this is a service YAML file. Okay, and one deployment which contains a set of pods communicate with another deployment, which is another set of pods, via cluster IP service. That means a virtual and static IP. So basically this is a deployment. So this is deployment 1, deployment 2, and deployment 3. So if deployment 1 wants to communicate with deployment 2 and deployment 2 wants to communicate with deployment 3, they have to communicate via a cluster IP service. So that's how you can check the actual IP address of your cluster IP service. The command is kubectl get service. How a service and deployment are linked, how the system knows where to map with which deployment to map the service. Okay, so if we are exposing it via command, we specify the deployment. But if we are not exposing via command, if we are creating via the YAML file, so the service will have the same selector as of the label of the deployment. Remember this rule. That's how these two objects are linked. So the label which is present in the deployment is same selector, exactly same selector should be present in the service. And if there are more than one deployments which has same labels, then the service will be linked with all those deployments. Remember. Now let us discuss load balancer service. So if you consider this diagram as our cluster setup, so in this diagram you can see we have three nodes, three worker nodes. So this is worker node 1, worker node 2, worker node 3, and in every worker node you have a pod. Okay, and basically these pods are replicas of one deployment only. I mean replicas in one deployment. So this is a pod with a label app my app, and another copy here, another copy here. So you see the IP addresses are different on different nodes, and the port is port 80. Okay, and here is the service, right, with selector my app, same selector, my app. Now I want to access these pods from outside the cluster. So you see one more thing, that the pod IP range is 10.120. The node IP range is 192.168. Okay. So now I want to access, in the earlier section, I have accessed this pod from this pod, something like this. So I have accessed this pod from a pod which is already present inside the cluster. But this time I want to access this, any one of these pods from outside the Kubernetes cluster. Okay. So for that, first I need to create a load balancer. Okay. A load balancer service here, and a load balancer software or a load balancer component will be first created outside the cluster. That means outside these worker nodes, and the load balancer will have its own IP address. So you see, this can be of the range of from the range of the nodes, worker nodes, or similar to it. Okay, it depends how the configuration, how the system has been configured, and what the external user will do. Okay, so we, in this case, we have to create a load balancer service. So the kind is still service. The only difference is the type is now load balancer. So in the earlier definition, you must have seen that there was no type field. So remember, if type is not mentioned, then by default, it is cluster IP service. So the default type of the service is cluster IP. When you mention the type, it is that particular type of service. So here it is load balancer service. I need a port and a target port. So the port is 8080 and target port is 80. Okay. And the external user, how it can access this any of these pods. So the external user will be connected via internet to this Kubernetes cluster, and what he will do in his browser is curl http colon the IP address of the load balancer, which is actually an externally routable IP address. Okay, so IP address of the load balancer he will give, and with the port number of the service. So the port number of load balancer service is 8080. So if I hit this particular sequence, this particular web address, then I will be able to access any of these pods here. So this is the standard way to expose an application outside the Kubernetes cluster. Okay, so inside the cluster we have cluster IP, and outside the cluster we have to create a load balancer service. In private Kubernetes clusters, we have to configure a load balancer, any of the standard load balancers that are available in the market, like HA Proxy, Apache, or anyone else. And you have to use those load balancers as your external facing component towards the internet. Okay, so the user access the application using the load balancer IP via the port, and this time if we see the kubectl get services output, so we get a load balancer type of service along with an internal and an external IP address. Okay, let us understand about the last service type, which is node port service. So here, this is also a method to access any of the pods from outside the cluster without using the load balancer. Why? Because if you keep using load balancers with every service, there will be more number of load balancers required in your system, and every load balancer has a cost, especially in the managed Kubernetes platforms. So you cannot afford to have a large number of load balancers for your applications. So there are some components or some application components which can be accessed without using load balancers. So consider this setup wherein we have three pods here. Okay, so pod 1, pod 2, pod 3, and let's say all of them are present in one node only. So this is a single worker node, for example. This worker node might have a single replica also, or two replicas. Here it is just for representational purpose, it is shown three replicas in single worker node. Okay, now if I want to access this particular any one of these pods, so how I can access them? Okay, so as let's see this particular YAML file. In this service YAML, two things are different. The type is node port, you see, and there is a third type of port added here, which is node port, and that node port is 31000. This 31000 is the physical port is the port of the physical worker node. Okay, not for any service or any cluster IP service or any load balancer, nothing. This port number 31000 is actually the port number of the worker node, okay, which is open to access this particular service. So in this case, if a user wants to access the any one of this pod, so he can curl HTTP with node's IP address. You see here, instead of using load balancer IP address, what we can use the externally routable IP address of the worker node itself, which is 192.168.1.1 in that case, and colon with port number 31000. So this port number should be opened at the server level, and with this port and this IP address we can access the pods. Okay, so the user will access the application using the worker node IP via a port. Okay, and if I list the services, what I see is the web service 2 is node port type, and there is no external IP for the node port service because it assumes that you will use the IP address of your worker node. Let us understand microservices, which is one of the most talked buzzword in today's time. So there is a reason why I have put this section just after the completion of Kubernetes services. So most of the people think, like the people who are not familiar with Kubernetes, they think somehow that microservices are the same things as Kubernetes services. Okay, but that is absolutely incorrect. So what are microservices? We will understand here. So let us assume this architecture of an application. So this is an example from a shopping store website. So this blue box is your e-store UI. That means the web page with which the user interacts. And apart from the web page, the UI, you have a catalog service, you have an order service, and you have a payment service, right? So, and the whole application has a common database, right? So here you can see every component, product, order, payment, the UI is a part of a single code, okay? And you have a single database. This is called as monolithic architecture or old-fashioned architecture used in earlier times. Okay, we still have some applications like this, unfortunately, but this is called as monolithic architecture. Why monolithic? Because you have a single code which makes it complicated to understand. Okay, so whether it has been developed by a single developer or multiple developers, but the code base is a single file or a single code basically. Okay, this is very less fault tolerance and very difficult to maintain. Why? Because if you have problem in any of the components, you have to fix the whole code. Okay, you don't know whether the problem is because of this component or that component or this component, right? Big single database. If the single DB is gone, I mean, you have all the states preserved in a single database. If there is some problem in this database, then it is very difficult to restore this. Scaling and deployment challenges, right? Why? Because when you have single codes or monolithic kind of components, it is very difficult to scale them because you have to scale all the components together, multiply all of them together. Okay, and all the components are not compatible with the quick scaling on the infrastructure. And this is extremely difficult to change technology or language or framework. Let's say if you want to recode this application from Node.js to some other language, let's say Python, or from Python to R, or from R to anyone else, like, right? So that thing is very much difficult because you have all your catalog services under one code. Okay, so if one component you are successful to code into another application, another language or framework, It doesn't mean that the other component will also be able to get adapted with that. Okay, so these are some challenges of monolithic architecture or monolithic kind of application. So to resolve this, they have come across with this kind of architecture. This is called as microservices architecture. So now you have your same shopping site, okay, and there are some smaller services, okay, which are available. So remember, these services means here these services are not technical. So these are components, separate software components. So in place of a single code, now you have small pieces of code, independent and easy to manage. So this is one code, catalog service. This is another code, cart service. So four developers can work simultaneously on their part of code and develop the code in any language or any framework of their choice. Okay, very easy maintenance because single service won't make whole system down. Now let's say if you have a problem in this service here, catalog service, and this is down, then there should not be the problem with rest 3 of the services. Okay, and you will be easily able to identify that, okay, this particular service has some problem and you can fix that. And every service has its own database, so separate small databases for each microservice. So just like the codes, if you have a problem in one of the DBs, you can fix it. Okay, scaling and deployment is easy. Let's say you want to scale only the catalog service. So the problem here is you cannot scale only the catalog service. You have to multiply the whole code together. Okay, but here you can only scale the order service. You can make the catalog service up and down up to the multiplication factor of your choice. Okay, and every service can be coded in any language or framework, because finally you will have container images and you can run different container images onto your infrastructure. So understanding from this kind of example, I can say that microservices is not a technical term. It is more of a business or a design context. Okay. So in business terminologies, I mean, these services are called as microservices. Okay. They should not be confused with the Kubernetes services, which is purely a technical object. Kubernetes service is a technical object. Microservice is a business object. Okay. So when the business managers or the business development managers uh, imagine an application for their business, they talk in these terms that, okay, this particular application will have these much services and those services has a business relevance, okay, or a design relevance. In that context, they will be called as microservices. Okay. Now let us understand microservices in telco context. So this is a typical telecom application wherein we have a UI and we have components like tracing, logging, performance management, O&M, and other functionalities. This is kind of side components, and the main components of any telecom application are the signaling agents and the traffic agents, and they all have a common database. So this is the monolithic architecture of telecom applications, which we are familiar with. Okay, if you log in into any of the telecom node, may it be VoLTE, EPC, your old legacy RNCs, BSCs, GGSN, SGSN, all have almost similar kind of architecture. Okay, but now when telecom applications are also evolving towards microservices, so they will also have a change in the architecture. So beyond the UI, now you have separate component in Kubernetes terms, separate deployment for tracing, for OAM, okay? Or in VNF terms, these are your VMs, right? So you have OAM VM, you have some VMs for performance, some VMs as signaling agent, some VMs as logging agent, right? So you have different components now, okay? And each component has its separate database, okay? So that's how a telecom application has been migrated from monolithic to microservices architecture. Okay. When this application will be deployed on Kubernetes, so it is like These are your deployments. Deployment number 1, 2, 3, 4, 5, 6, and these are your stateful sets, all the databases. Okay, and all of them together will be called as an application.
Before going into our demo section, let's take a look at two other types of objects in Kubernetes, jobs and cron jobs. Similar to deployments and services, these objects create a pod, but the pods they create are different in terms of their lifetime. Normally, Kubernetes pods that are created by objects like deployments and services for our applications run basically forever unless Kubernetes terminates them or they crash. But what if we want to start a workload that we want to start up, run it to completion, and then exit? For this purpose, we have a new object type in Kubernetes called job. With this kind of object, we can start a container, run it for a certain period of time, and exit with a successful code. If the run is not successful, Kubernetes will restart the pod based on its restart policy, which by default is retry forever. These objects are handy for many things. For example, what if you wanted to run a script that logs into a database and updates some tables or manipulates some data and exits? With job objects, once the pod that we created completes its task, the pod stops, but it will remain in Kubernetes so that we can go check the logs and check the output that the pod created if required. Here is an example of a YAML file that we can use to create a job object in Kubernetes. The kind is job. We call the object pi because we plan to use it to compute the pi number to the 2000 decimal digit precision. Under template, we see the pod specifications for the pod that will be created. The image is paired, which basically is a general image that has paired software installed inside the image. And under the image, with this command attribute, we are passing a pair command we are feeding a pair command to the image as soon as the pod starts. So what happens is that when we deploy this job, a pair container starts running in a pod. It starts running this command immediately, which calculates the pi number for us to the precision of 2000 decimal digits and returns the result with a successful return code. Another kind of object that we have in Kubernetes is cron job. It has all the capabilities of a Linux cron. It basically allows us to schedule and run jobs at a specific time or at a repeated interval. How does the template for a cron job look like? As you see here, the kind of the object that is created by its template is cron job. The schedule part is what you might be familiar with from Linux. This notation, this syntax means that the job is scheduled to run every 1 minute. So basically, if you want to run this second parameter specifies which hours of the day we want to run the task, and this one which days of the month, which months, and which specific days in a week. Basically, this is the syntax in a nutshell. So this syntax means that every 1 minute we want this cron job to create a pod for us and run that pod. And what is that pod which is being run? The specifications are provided here under the spec. Basically, it's a BusyBox image, which is a kind of a Linux operating system image. The name of the container is hello, and As soon as we start the container in the pod with this image, we pass these parameters to the container. Basically, we run a shell inside the container and um, get the date and type this message echo hello from the Kubernetes cluster. And basically, once this task is completed and this command is being executed, this hello message is printed, the job terminates. But the next minute again, because of this schedule section, the next minute again, a new pod is being created. Note that the cron job retains only the three last successful pods and the last failed pod for us. So although here we are creating a pod every 1 minute, but Kubernetes doesn't keep all the pods for us. It only keeps the last three successful pods and the last failed pod for this cron job.